Hello, this is Philip Myers of PEMY Consulting. Welcome to Strength of Materials for Tank Engineers, Part 11. Earlier in the series, we reviewed the basic principles of the Mohr Circle, which provides insight about how stresses behave at a point in a material subjected to an internal stress state. Since failure of ductile materials like steel often occur by shearing stress failures, it's important to understand how shear stress and maximum normal stresses or principal stresses relate to each other. Because a 2D Mohr circle only captures the stress state strictly within the plane of consideration or in the XY plane, we will find that the absolute maximum shearing stress is not always given by the 2D Mohr circle. The easiest way to understand how the maximum 2D plane stress can be exceeded, and which is called the absolute maximum shearing stress, is with a so-called 3D Mohr circle. Even though it's called 3D, it's really just 3 rotations about the 3 axes and the 3 resulting 2D Mohr circles. I'll show you what I mean next. So let's review the 2D Mohr circle. It's a graphical way to visually understand how the stress transformation equations work as the 2D stress element rotates about an axis, in this case the z-axis. Up until now we have rotated about the z-axis so we could examine the 2D stress state in the xy plane. The Mohr circle helps us visualize the relationship between normal and shear stresses, which change with direction or rotation angle theta. Recall that the stress square element is like a limit in calculus. The stress element size gets smaller and smaller so that it can be used to approximate the properties at a point, which is infinitely small. Yet surprisingly, at least to me, direction matters for stresses even at a point of 0 size. For plane stress, we have at any point 3 independent stresses, 2 normal stresses, sigma x and sigma y, and 1 shear stress, tau xy, which all live on the perimeter of the Mohr circle. The arbitrary plane stress element is rotated about the z-axis until the shear stresses on the xy faces vanish. At this angle, theta, in the stress element, the shear stress is 0, but the normal stresses are maximized. These maximum normal stresses are called principal stresses. As the rotation of the stress element goes from 0 to pi, the 2D Mohr circle goes from 0 to 2 pi. After that, the stress state repeats as the angle theta keeps increasing. Note that in the Mohr circle, we take positive tau down, and this makes the rotation in the stress element and the Mohr circle both counterclockwise. The first step in developing the Mohr circle is to plot sigma x and tau xy for the x and y face normal stresses. After that, the radius of the Mohr circle can be determined, and the radius is the magnitude of the shearing stress. While the angle of rotation can easily be computed as shown in our earlier models, we are interested in the absolute maximum shearing stress to make sure that we are not approaching a shearing stress failure. So far, we've always rotated about the z-axis to obtain the 2D Mohr circle for the in-plane xy stress state. By doing so, we have found the maximum shear stress in the xy plane, but this may not be the absolute maximum shear stress. To find out if the absolute maximum shear stress exceeds the in-plane stress state, we must rotate about the other 2 axes as shown. This graphic shows what I mean by rotating the stress element about the other 2 axes. Let's first make sure we understand the coordinate system, which is now shown by the x, y, and z axes. Even though we represent the plane stress element as a square, it's really still a cube. But the z direction principal stress is 0, and the x, z, and y, z shear stresses are also 0. There is some orientation for the stress element where there are no shearing stresses on any of the faces. If we draw a principal stress axis and plot the principal stresses P1, P2, and P3, and note that P3 is 0, that is the principal stress or normal stress in the z direction, we see that there are really three Mohr circles. The 2D principal stresses are sigma P1 and sigma P2, like we have done before. In this case, both principal stresses are tensile, and the third principal stress, sigma P3, is 0. The small circle to the right shows XY plane principal stresses, with the radius being the maximum shearing stress in the XY plane. But you can see that there are two additional red Mohr circles for the XZ and YZ planes as well. In this case, the Mohr circle with the largest radius between sigma P2 and sigma P3 gives the absolute maximum shearing stress, and it's in the YZ plane, so it occurs out of plane from the XY plane. Recapping, after plotting the 2D Mohr circle for rotations about each of the three axes, the maximum radius of the three Mohr circle radii is the maximum shearing stress occurring in the stress element. So it is really always necessary to find the three Mohr circles to make sure that you are aware of the absolute maximum shearing stress. For the three principal stresses shown, it is clear that the absolute maximum shearing stresses occurs as the radius of the sigma P1 and sigma P3 circle as shown. The absolute maximum shearing stress occurs at 45 degrees between the X and Z planes and has a magnitude of 1/2 of the difference between sigma P1 and sigma P3. After you do a lot of these 3D Mohr circles, you realize that there are three possible cases for the 3D Mohr circle. Two of these cases result in an absolute maximum shearing stress that occurs out of plane from the three normal planes. This occurs when the largest circle does not involve the 2D principal stresses sigma 1 and sigma 2 as in the left two diagrams. In the right diagram, the largest 2D Mohr circle is in fact the maximum shearing stress, and thus it occurs in plane. Notice in cases 1 and 2, both principal stresses are of the same sign. In case 3, they are of the opposite sign. When the signs are the same, that is when the principal stresses are both tensile or both compressive, the maximum shear stress is just 1/2 of the maximum principal stress magnitude. In the third case, where the principal stresses are of opposite sign, the absolute maximum shear stress is the difference between the principal stresses. Rather than figure out stresses as we did on the previous slide, there's a simpler way. Just order the stresses from largest to smallest. Then the absolute maximum shear stress is always indicated as 1/2 of the largest less the smallest stress. Naturally, when one of the principal stresses is positive and the other is negative, the absolute maximum shearing stress will be greater than 1/2 of any of the principal stresses. The simplest way to handle the absolute maximum shearing stress using the three Mohr circles is to just order the stresses from largest to smallest. So in our three cases, we have the largest, which is sigma 1, less the smallest, which is sigma 3, and sigma 3 is 0, of course, so the absolute maximum shear stress is just sigma 1 over 2. In the case where both stresses are negative, we do the same thing. We take sigma 3 minus sigma 2 divided by 2, and the absolute maximum shearing stress magnitude is sigma 2 over 2. In the case where the signs of the principal stresses are opposite one another, for sigma 1 and sigma 2, we also take sigma 1 minus sigma 2, which is the minimum stress, divided by 2. Because of the sign of sigma 2, sigma 1 minus sigma 2 is the radius of the big circle. Our understanding of the Mohr circle is now sufficiently complete that we can understand the maximum shearing stresses in pressure vessels. To review, we started with a plane stress element and rotated it about the z-axis to determine the principal stresses and the maximum shear stress in the xy plane. But we learned that the radius of the Mohr circle, which is the maximum shearing stress, is not always the absolute maximum shearing stress in the stress element. This is because even a plane stress element is really a cube with a principal stress in the z direction equal to 0 and no shearing stresses on the z faces of the stress element. Because there are always three principal stresses, and even though sigma P3 is 0, the absolute maximum shearing stress may not occur in the XY, YZ, or XZ planes. It may be at 45 degrees to one of these three planes. Next time we'll focus on pressure vessels and absolute maximum shearing stress. Thank you.